Okay, so here's an example of a problem that uses conservation of energy and conservation of momentum. So what we have is someone who's swinging down from a rope. So that's kind of essentially kind of coming down like a pendulum. He's going to hit the bad guy. Well, it's a stuntman and another actor, I guess, the villain. He's going to hit him at the bottom of his swing, and they're going to intertwine and move off as a single object. And our job is to figure out how fast they move after the collision. So just kind of trying to sketch out what this looks like. So we kind of start up here and swing down. And I'm going to call the stuntman person A and the villain person B. So this is the initial position where the person's going to have, the stuntman's going to have all potential energy. And this is the final position. So here, person A is going to move with some initial velocity. And there's where he has all his kinetic energy. He's going to hit person B, who has an initial velocity of 0. And then after the collision, the two are going to move off as a single object with some final velocity. So here we have the conservation of energy. And then in this area, we're talking about the conservation of momentum. So applying the conservation of energy is going to allow us to figure out how fast the stuntman is moving when he hits the villain. So for that case, this is going to be my initial point up here, and down here will be my final point for the energy conservation. So I'm saying initial energy equals final energy. There's no talk of any non-conservative forces. Initially, he's just starting from rest, so he doesn't have any kinetic energy. His potential energy will be given by mgh. When he goes to his final point, he doesn't have any potential energy. He has all kinetic energy. So this is a situation where all potential energy is converted into kinetic energy. Notice the mass of the stuntman is irrelevant, and if we solve for velocity, it's the square root of 2gh. So g, of course, is 9.8, and he left from a height, here we see, 5 meters. This gives us a initial velocity that he's moving with when he gets to the bottom of his swing of 9.9 meters per second. This is going to correspond to the initial velocity of him for the purposes of looking at this from the viewpoint of conservation of momentum, the second part of this problem. In the second part of the problem, we have the stuntman is moving with a speed of 9.9 meters per second. He's going to hit the villain, who's not moving at all, and then the two will move off as a single object. This is a perfectly inelastic collision. So my initial x momentum is equal to my final x momentum. Because we're told that his velocity is horizontal when they collide, that's why I can just say we deal with momentum in the x direction. So looking initially, I would want to say, does object A, which is the stuntman, have momentum? That would be given by its mass times velocity. I also look at the villain, which is person B. His momentum will be mass times his velocity. But remember, he's initially motionless, so that term just goes to 0. Remember, we said this is perfectly inelastic. And so after the collision, the two objects are a single object, so the total mass of the two added together times the final velocity. So if I put values in here, the stuntman had a mass of 80 kilograms. He was moving with a speed of 9.9. We have 80 plus 70 is the mass of the villain, times V final. So V final is 80 times 9.9 divided by 150. And so we find the final velocity that they move off with is 5.28 meters per second. And that's it.